Everybody, today I am going to discuss methods of preparation and properties of alkanes. Already we have seen its general formula is CnH2n plus 2, where n value starts from 1, 3 and so on. So far functional group is concerned, do not possess any specific functional group. Now here each carbon atom undergoes sp3 hybridization. Now usually alkanes exhibit chain isomerism. Next I am proceeding to different methods of its preparation. Now from different source we get alkanes. Number one source is your alkyl halide, whose general formula is Rx. For alkane we can write RH because R is CnH2n plus 1 hydrogen atom when added to it we can get alkane. From alkyl halide there are two methods of preparation, bit 1 by reduction. When alkyl halide is reduced by zinc copper couple in presence of ethanol, we get alkane having same number of carbon atom as that of alkyl halide. There is no change in number of carbon atom. Zinc copper couple means zinc metal is wrapped by copper, where zinc react with ethyl alcohol, two molecules of it react to form C2H5O2 zinc ethoxide plus hydrogen. This hydrogen so produced will reduces alkyl halide. This is symbol for reduction. Two hydrogen atom forms RH and HX. This is your alkane. If you start with same ethyl chloride, same, that is by reduction, where hydrogen atom adds up, it will give you methane plus HCl. So there is no change in number of carbon atom. Zinc metal react with ethyl alcohol, produces hydrogen, copper act as a catalyst here, alkyl halide reduced to alkane and HX. The second way of getting alkane from alkyl halide is by Woods reaction. Woods is the name of a scientist, Woods reaction. Here two molecules of alkyl halide combines in presence of metallic sodium and dry ether to form an alkane having more number of carbon atoms than that of alkyl halide. This reaction is called Woods reaction. Two molecules of alkyl halide, say Rx, combine with sodium, two molecules I have written, in presence of dry ether. This is most important, you must mention, otherwise you will not get mark. Here 2 molecules of sodium halide is removed. You are getting R and R, which is an alkane. Say for example, if we take say methyl chloride, sodium, or in presence of dry ether, there is elimination of sodium chloride and you are getting ethane. So you can see number of carbon atom increases. Now what is the function of dry ether? Dry ether. Ether having no water is called dry ether. Now usually alkyl halides are contaminated with water. They are liquid, sometimes contain water. Now sodium react with cold water to sodium hydroxide, it forms sodium hydroxide and hydrogen. These two products form reacts with alkyl halide. Alkyl halide react with sodium hydroxide, gives you sodium halide plus alcohol. The hydrogen produced also react with alkyl halide to form RH, but here the number of carbon atom is not changed. So these two products are not in accordance with Wood's reaction. Wood's reaction aim at to get more carbon atom. So you shall have to avoid the contact of sodium with water, for which we take dry ether. Now the organic compound, that is alkyl halide, comes to ether layer, which is lighter, and water layer remain bottom. So sodium react with the alkyl halide only, it does not get any opportunity to react with the water. So therefore we take dry ether. Remember this method, methane cannot be prepared by this method. Only number of carbon atoms increases. The second way, from monocarboxylic acids, there are also two processes. Bit 1, decarboxylation. D means removal. Carboxyl group will be removed. When you are taking sodium salt of monocarboxylic acid, heated with soda lime, sodium hydroxide calcium mixture is called soda lime. Soda stands for sodium hydroxide, lime water stands for calcium oxide. You will get an alkane having 1 carbon atom less than monocarboxylic acid. 1 carbon atom decreases. So here you will get sodium carbonate plus alkane, 1 carbon atom, calcium oxide remain as such. So therefore it is called decarboxylation, because carboxyl group is removed when heated with sodium salt of the monocarboxylic acid, heated with soda lime. Soda lime is a mixture of sodium hydroxide and calcium oxide. You get 1 carbon atom less than the monocarboxylic acid. If you start with say 2 carbon atom, say sodium ethanoate, you will get, on heating with soda lime, which is a mixture of sodium hydroxide and calcium oxide. Here is elimination of one molecule of sodium carbonate. You are getting methane, having one carbon atom less than the acid. So you are getting one carbon atom less here. If you want to get 5 carbon atom alkane, you will start with 6. If you take 10 carbon atom acid, you will get 9. So this is one method. Sometimes this method is called Dumas method. Decarboxylation is sometimes called Dumas method. Second way is by Kolb's electrolysis. Remember, Kolb's electrolysis is a general method for the preparation of alkane, also alkene, also alkyne. We can get all hydrocarbons by Kolb's electrolysis process. Here what we take? A saturated aqueous solution of either sodium or potassium salt of monocarboxylic acid. Monocarboxylic acid on electrolysis gives you an alkane having only even number of carbon atom. That means you can get ethane, butane, hexane, etc. So when you are taking a saturated aqueous solution of either sodium or potassium salt of monocarboxylic acid on electrolysis gives you alkane having even number of carbon atom. Let us take, say, potassium alkanoate. Electrolysis is a reversible process. Electrolysis, you will get carboxylate ion plus potassium ion. This is your carboxylate ion and potassium ion. Reaction at cathode, potassium ion add up with electrons gives you potassium metal, which react with water gives you potassium hydroxide and hydrogen. So hydrogen will be liberated at cathode. At anode, the reaction is two-step. The carboxylate ion, 2 molecules I have written here. At first it loses 2 electrons, then it loses 2 molecules of carbon dioxide. You will get R and R, that is alkane. It is removed at anode, liberated anode. Now you can see carbon dioxide is a gas. It reacts with potassium hydroxide, gives you potassium carbonate plus water. So carbon dioxide is arrested. We call it is arrested by potassium hydroxide, arrested by, that is remain there. So when sodium or potassium salt of monocarboxylic acid is electrolyzed, you get alkane having even number of carbon atom. I am giving one example. Say this is your potassium ethanoate. You can see total carbon atom is now 4. Electrolysis is a reversible process. Electrolysis, you will get acetate ion or ethanoate ion plus potassium ion. Cathode reaction remains same. Potassium ion react with, add up with 2 electrons, gives potassium metal. Potassium metal react with water, gives you potassium hydroxide and hydrogen. Now at anode, I am taking that ethanoate ion, that is CH3 COO minus, At first step, it loses electron. In the second step, loses carbon dioxide. So you are getting ethane. You can see I have started with altogether 4 carbon atoms. 2 of them removed as carbon dioxide. You can getting ethane having even carbon atom. You will start with say 6 carbon atom. 2 carbon dioxide molecules will be eliminated. A will be removed, and you are getting 4 carbon atom alkane, that is only even number. Carbon dioxide is never removed at cathode or anode. It is arrested by potassium hydroxide forming potassium carbonate water. In this method also you cannot get methane. Odd numbers you can't get. So this is another way of getting alkanes from monocarboxylic acid. The third process is from by hydrogenation. Hydrogenation means hydrogen will add up. Hydrogenation of unsaturated hydrocarbons. Unsaturated hydrocarbons means alkanes or alkenes. This method sometimes called Sabatier and Sandren's method. Now here Sabatier's and Sandren's method. Now here alkene or alkyne is treated with current of hydrogen gas in presence of nickel catalyst between 200 to 300 degrees centigrade, or you can take platinum or palladium as catalyst at say 25 degrees in low temperature here sufficient. So alkenes, you will take ethene. On hydrogenation it will give you ethane, or here I have taken ethene. So when alkene is heated with the hydrogen in presence of nickel catalyst between 200 to 300 degrees centigrade, or platinum palladium as catalyst at 25 degrees centigrade will give you alkane. If you take a triple bond containing compound like say ethine, the reaction will be 2-step. Same condition I have written, therefore I have written do. It will first form alkene, that is ethene, then it is again hydrogenated to ethane. So you can say the double bond is saturated to single bond, triple bond first step to double bond, then to single bond. Here addition of hydrogen takes place, therefore process is called hydrogenation. So this is another way, but here also you cannot get methane because methane contains 1 carbon atom. Any alkene or alkyne minimum number of carbon atom will be 2. So this method does not give also methane. So this is another method. Also we can get alkane by using Grignard's reagent. Grignard reagent. That is your alkyl magnesium halide is called Grignard reagent. RMgX. R is alkyl group, X is halogen. When Grignard reagent treated with compound having active hydrogen atom. Active hydrogen atom means when hydrogen is attached to either to oxygen or to nitrogen or to sulfur, then hydrogen atom is called active hydrogen atom. When any Grignard reagent treated with compounds containing active hydrogen atom, that means hydrogen attached to either oxygen or nitrogen or sulfur, you will get alkane. Say for example, you will take water and a Grignard's reagent say RMgX, you are getting RH, which is an alkane, plus you are getting magnesium hydroxy halide, magnesium hydroxy halide. Or if you will take say one alcohol which also contain active hydrogen atom, on treatment with Grignard's reagent, you will get alkane RH, and you are getting magnesium alkoxy halide, magnesium alkoxy halide. So these are your alkane. So this is another way of getting alkane. When hydrogen attached to either oxygen or nitrogen and sulfur, we call it active hydrogen atom. That hydrogen atom react with alkyl group of Grignard's reagent, that is alkyl magnesium halide, give you alkane. Another important method is your Corey-House synthesis. Corey-House synthesis. Now, during this method or during this process, alkyl groups up to different alkyl halide. In Wood's reaction, we have taken same alkyl halide, but here two different alkyl halide couples in presence of metallic lithium and cuprous iodide forms an alkane having odd number, or we call it unsymmetrical alkane. The steps of the reactions in this method: one alkyl halide is converted to alkyl lithium, which react with cuprous iodide to form lithium dialkyl cuprite. It is then treated with another alkyl halide when form unsymmetrical alkane. I am explaining with example. If we take say methyl iodide, when treated with lithium, it forms methyl lithium or alkyl lithium, methyl lithium and lithium iodide. Now this methyl lithium, that is alkyl lithium, methyl lithium react with cuprous iodide. Here I have taken two molecules. When it will form CH3 whole to Culi. Its name is lithium dimethyl cuprite, and you will get cuprous, and you get lithium iodide. Now this lithium dimethyl cuprite again will react with another or different alkyl halide. I have taken here one is methyl iodide, I have taken ethyl iodide. When you will get propane, that is an unsymmetrical alkane, propane, and you will get methyl copper plus lithium iodide. This is methyl copper. So I am repeating the Corey-House method. In this method, now two different alkyl halide couples in presence of metallic lithium and cuprous iodide. When you get an ultimately alkane having odd number of carbon atom, we call it unsymmetrical alkane. We call it unsymmetrical alkane. Now steps of the reaction. Now one methyl alkyl iodide react with lithium when for alkyl lithium. Here you get it methyl lithium. That alkyl lithium react with cuprous iodide to form lithium dialkyl cuprite. Here you are getting lithium dimethyl. Here alkyl group is methyl cuprite, and that lithium dialkyl cuprite again react with the other molecule of alkyl iodide. Here I have taken ethyl iodide. When you are getting propane, which is an unsymmetrical alkane. Similarly, you can get pentane. Say for example, in order to get pentane, you can treat it, say ethyl bromide and say propyl bromide. So remember, during Wood's reaction, two alkyl halides they also mix, but there the alkyl halides are same, but here the alkyl halides are different. So in this method also you can get methane, you can get propane, pentane, heptane, etc. So this is all about the different methods of preparation. What you have noticed, in some methods you are not able to prepare methane. So to get methane, preparation of methane only. There are two methods. When aluminum carbide treated with water, aluminum carbide will be Al4C3. When treated with water, it will form aluminum hydroxide and methane. So when aluminum carbide treated with water, you are getting aluminum hydroxide methane. Another method, from carbon monoxide. When carbon monoxide treated with hydrogen in presence of nickel catalyst between 300 to 500 degrees centigrade, you get methane plus water. So these are the other two methods for the preparation of your methane only. Either you treat aluminum carbide with water or carbon monoxide with hydrogen. Here nickel acts as a catalyst at a high temperature between 300 to 500 degrees centigrade. So these are the all different methods of preparation of alkane, including separately the methane. I am not going to discuss the physical properties, only states I am telling. So far their state is concerned. Carbon atom 1, 2 till carbon atom having 4, that is till butane. These are gases. Carbon atom 5 to carbon atom 17, these are liquids. And carbon atom 18 onwards remain in solid states, solids. So gaseous hydrocarbons saturated one is carbon atom 1 to 4, liquid one carbon atom 5 to till carbon atom 17, solids will be carbon atom 18 onward. Now already I have told you in type of chemical reaction connection with that, it undergoes substitution reaction. So far chemical reactions are concerned, substitution reaction. Now there are 3 substitution reactions. One is halogenation, number 2 nitration, number 3 sulfonation. So 3 different type of substitution reactions are exhibited by alkanes. They are halogenation, nitration and sulfonation. To start with, let us discuss halogenation. The rate of reaction of halogen, fluorine, is greater than speed of the reaction, greater than chlorine, then bromine, then iodine. It is observed the reaction of fluorine, chlorine, bromine is one hand, iodine is the other hand. So, the rate of reaction fluorine is greater than chlorine and greater than bromine than iodine. The reaction of iodine is a little different than that of fluorine, chlorine and bromine. Again, this fluorine, chlorine, bromine and iodine, they react in two different conditions. One is in presence of diffusion light, the sunlight available inside the room. Another in presence of direct sunlight. Direct sunlight is outside the room. So now let me start with the reaction of halogens in presence of diffuse sunlight. We will take say methane with chlorine in presence of diffused sunlight. Here this reaction is multi-step. Multi-step means it proceeds till all the hydrogens get replaced by chlorine. So it is a multi-step reaction. You will get say chloromethane plus HCl. This is your chloromethane. You will start with methane, which contains 4 hydrogen atoms. So reaction will be 4 steps. Again it will form dichloromethane and HCl. Dichloromethane. Again it reacts with chlorine to form trichloromethane and HCl. Trichloromethane. Also we call it chloroform. Common name is chloroform. Again it reacts with chlorine, forms carbon tetrachloride or tetrachloromethane, or we can call it carbon tetrachloride. So reaction proceeds stepwise. Since it contains 4 hydrogen atoms, 4-step reaction gives you chloromethane, dichloromethane, trichloromethane and tetrachloromethane. Similarly, if you take ethane, which contains 6 hydrogen atoms, reaction will be 6-step. That is, it is a multi-step reaction. Now this reaction proceeds by free radical mechanism. Free radical mechanism. So chlorine in presence of H stands for sunlight. So it undergo homolytic fission, gives you 2 chlorine free radical. Methane also breaks to give you methyl free radical and hydrogen free radical. Methyl free radical react with chlorine free radical to form chloromethane. Hydrogen free radical also react with chlorine free radical to form HCl. So this is the mechanism called free radical mechanism. So in presence of sunlight, chlorine free radical produce, methane also produce methyl free radical, hydrogen free radicals. Methyl free radical react with chlorine free radical, form chloromethane. Hydrogen free radical, chlorine free radical react to form HCl. It is asked sometimes by this process ethane is produced, because sometimes methyl free radical they combine to form ethane. So sometimes this process also produces ethane, because 2 methyl free radicals sometimes combine to form ethane. So this is when alkane treated with halogen in presence of or in presence of diffuse sunlight available inside the room. In presence of direct sunlight, say it will take methane plus chlorine, direct sunlight, it's direct sunlight, you will get carbon and HCl. So this is regarding the reactions of one hand fluorine, rate of reaction will be faster than chlorine, chlorine will be faster than bromine. But when treated with say iodine, the reaction is reversible. It will form methyl iodide and HI. So therefore direct iodination of alkane is not carried out. Sometimes ask why? Because the reaction is very, very slow and reversible. Reaction is slow, very, very slow and reversible in nature. Therefore, direct iodinations of alkane usually not being carried out. This is regarding your halogenation. Next I shall proceed to nitration. Nitration is carried out by nitric acid. If you are taking alkane, nitric acid I can break into HNO3. This is your nitric acid. Here there is one removal of one molecule of water and you are getting nitroalkane. Though theoretically all alkanes can be nitrated, but it is hexane and higher members are easy to nitrate. Why? Because both hexane and nitric acid, they remains in same phase. Same phase means same state. Both of them are liquid. So reaction become better. So when hexane and higher member which are liquid treated with nitric acid, NO2 I have written HONO2, HNO3 I have broken it. It will give water and it will give you nitrohexane. So my point is that though theoretically we can nitrate all alkanes, but it is hexane and higher members are easy to nitrate because they exist in same phase, that is same state. However, recently vapor phase nitration are being carried out. Vapor phase nitration are being carried out. Nitration with lower members of alkane, say methane with filtered with nitric acid vapor between 400 to 440 degree centigrade. You will get nitromethane plus water. You are getting nitromethane. Similarly, if you are taking ethane with the nitric acid vapor at same 400 to 440 degree centigrade, you are getting nitroethane plus water. Nitroethane. But if you are taking propane, you are getting four different products. Say this is your propane. When it treated with nitric acid vapor between same 400 to 440 degree centigrade, 400 to 440 degree centigrade, you can get varieties of product here. This is your 1-nitropropane. Also it gives you CH3CH and NO2 CH3. This is your 2-nitropropane. Sometimes it also breaks to give you nitromethane, and water, and also gives you nitroethane and water. So you are getting different products here. So when propane is nitrated by using nitric acid vapor between 400 to 440 degrees centigrade, you can get 1-nitropropane, 2-nitropropane. With propane molecule may breaks to give you 1 carbon and 2 carbon atoms. You can get nitromethane and nitroethane. So this is regarding the nitration. Now so far the the last substitution reaction is sulfonation. It is also one-step process. When alkane treated with sulfuric acid, you will get, this is your sulfuric acid. I have just broken it, H2SO3H. After removing 1 molecule of water, you are getting alkane sulfonic acid. Though theoretically all alkane can be sulfonated, it is the hexane and higher members are easy to sulfonate because they exist in same phase. Sulfuric acid, they exist in same phase, that is in liquid state, liquid phase. So here you get 1 molecule of water plus hexane sulfonic acid. So this is all about the substitution reaction of alkane. Remember, with halogen, 2 different ways, fluorine, chlorine, bromine in one hand and iodine in another way. Again, fluorine, chlorine, bromine, they react under 2 different conditions. One is direct sunlight, another diffuse sunlight. Diffuse sunlight is multi-step process. Reaction proceed by free radical mechanism. Both nitration sulfonation is one-step process. Though all members can be nitrated or sulfonated, but it is hexane and higher members are easy to nitrate or sulfonate because they exist in same phase. However, recently we can carry out vapor phase nitration with lower member hydrocarbons like methane, ethane. Propane gives you different products. Next is oxidation. Oxidation. Number 1, combustion. When anything is heated in presence of oxygen, with oxygen we call it combustion. Here if you take an alkane, here carbon part is oxidized to carbon dioxide, hydrogen part oxidized to water, along with the evolution of heat which is used for cooking purpose or different price. Second, catalytic oxidation. When lower hydrocarbon are oxidized in presence of metallic copper as catalyst at high temperature and high pressure. Here we have taken temperature 400 degrees centigrade, pressure is 200 atmosphere pressure, it gives you alcohol, corresponding alcohol. Only lower hydrocarbons, methane, ethane, it gives you alcohol. Other members cannot be oxidized. Third, chemical oxidation. Alkane does not undergo chemical oxidation, that is acid fat, potassium permanganate or acid fat potassium dichromate cannot oxidize alkanes. However, alkanes having a tertiary carbon atom, that means carbon atom when it is attached to 3 more different carbon atoms. When this is oxidized, gives corresponding alcohol, say KMnO4 mixed with dilute sulfuric acid. Here the carbon atom, which is tertiary in nature, is converted to alcohol. This compound is 2-methyl propane. The tertiary carbon atom, which I am star marked, because that carbon atom is attached to 3 different carbon atoms. We get 2-methyl 2-propanol. So this is regarding the oxidation. When heated with excess oxygen, we call it combustion. When carbon part gets oxidized to carbon dioxide, hydrogen to water, along with the evolution of heat. Catalytic oxidation carried out only by lower hydrocarbons. Catalyst use copper, temperature 400 degrees centigrade, pressure 200 atmospheric pressure. And chemical oxidation means using chemical oxidizing agent. Usually it cannot oxidize. Alkane cannot be oxidized by chemical oxidizing agent except your alkanes having tertiary carbon atom. Next is cracking. When pyrolysis means breaking a compound by the effect of heat, When pyrolysis is applied to saturated hydrocarbon, we call it cracking. During this process, a higher saturated hydrocarbon is heated at high temperature, at high pressure, in presence of catalyst, but important, in absence of air or oxygen. In absence of air or oxygen, it breaks to lower hydrocarbons, may be saturated, may be unsaturated. Pyrolysis means effect when a compound breaks by the effect of heat. When we apply pyrolysis to saturated hydrocarbon, we call it cracking. Say, let us take C8H18, say octane. So, at a high temperature, high pressure, catalyst. So, this will decide what will it break. It can give you, say, C4H10, C4H8, or it can give you, say, C6H12 plus C2, say C2H6, or it can give you, say, C5H10 plus C3H8, or it can give you methane, it can give you ethane, it can give you carbon, hydrogen. So, varieties of products are obtained. All depends upon temperature, pressure and catalyst. Remember, you should not use air or oxygen, otherwise it will burn then and there, gives you carbon dioxide, water and heat. You cannot get lower hydrocarbons. Here lower hydrocarbon may be saturated or may be unsaturated. So, cracking a higher saturated hydrocarbon is allowed to break in presence of high temperature, pressure and catalyst. And the last reaction is aromatization. Aromatization means when we are getting aromatic compound from aliphatic compound. Here hexane and higher member. Hexane and higher member. You see, this is I have written hexane, there is no bond here. Hexane and higher member, when heated in presence of aluminum oxide chromium trioxide mixture at 600 degree centigrade and 15 atmospheric pressure gives you benzene. Or you can write benzene. Similarly, if you take heptane, you see there are 7 carbon atoms. So when heptane, under this condition, that means aluminum oxide chromium dioxide mixture at 600 degrees centigrade heated at 15 atmospheric pressure, you will get toluene. Here one of this hydrogen atom benzene is replaced by methyl group. So these benzene or toluene are aromatic compounds. So when hexane and higher members are heated in presence of aluminum oxide chromium dioxide mixture at 600 degrees centigrade and 15 atmospheric pressure aromatizes to give benzene. From hexane you can get benzene, from heptane you can get substituted benzene, that is your toluene. So this is all about alkanes. Next I am proceeding to alkene. So far the general formula is concerned, it is CnH2n, N value starts with 2, can be 3, 4, etc. Functional group, it contains a carbon-carbon double bond. Now here there may be carbon-carbon single bond, carbon-carbon double bond. The carbon atom having carbon atoms having double bond, not other one, having double bond undergoes sp2 hybridization. sp2 hybridization, and it usually undergoes position or exhibit position isomerism. So alkene general formula CnH2n, N value will start with minimum 2 carbon atom. Functional group is carbon-carbon double bond. Carbon atom having double bond will undergo sp2 hybridization and it exhibit position isomerism. Though I am going to discuss the general methods of preparation, but my emphasis will be on ethene. Ethene, its common name is ethylene. Number 1 method of preparation by dehydration, means water will be removed. Dehydration of alcohol. When alcohol is treated with dehydrating agents like aluminum oxide or phosphorus pentoxide at a very high temperature, 350 to 450 degrees centigrade, or you can use 75% concentrated sulfuric acid. Here temperature required is less, 140 to 170 degree centigrade. So your alcohol is dehydrated to for alkene. Say if you are taking ethyl alcohol, this is your ethanol. So 2 different dehydrating agents I have taken. If I take aluminum oxide or phosphorus pentoxide, temperature required bit high, 350 to 450 degrees centigrade, or you can take 75% concentrated sulfuric acid. Here the temperature is 140 to 170 degrees centigrade. So 1 molecule of water is removed to give you here ethylene or ethene. Ethylene is common name. Similarly, if you take propanol, 1 propanol or 1 propanol, under this condition, I am not writing always, do means these conditions, it will give you propene propene plus water. So both propene, but here both ethanol and propanol are primary alcohol. But if you are taking a secondary alcohol, or even if you are taking a tertiary alcohol, this is I have taken 2-butanol. When it is subject to the above condition, there can be formation of two products. It can either form CH double bond CH2, or it can form, this is but 1-ene, this is but 2-ene. Now this is being decided by which product will be more by a rule called Set-Jeffs rule. I'll tell you this one, Set-Jeffs rule. So you see, when along with water, any secondary alcohol or tertiary alcohol is subjected to dehydration, you are getting two different alkene. Here I'll tell you which one will be the more, which one will be the less. This is being decided by Set-Jeffs rule, because this is also applicable to my second method, that is called by dehydrohalogenation. Here both hydrogen and halogen is removed, therefore it is written dehydrohalogenation of alkyl halide. So if you take, say, ethachloroethane, which is a primary alkyl halide, treated with alcoholic KOH, that means potassium hydroxide dissolved in alcohol, you will get ethylene. HCl will react with potassium hydroxide, will give potassium water. Now 5 minutes. Similarly, if you are taking chloropropane in presence of alcoholic KOH, you will get propene, potassium chloride water. So these are the two different, these are two primary alkyl halide, but if one of them is secondary one or even tertiary one, I have taken here 2-chlorobutane. So when treated with alcoholic KOH, here also you will get but 1-ene, but 2-ene, which one will be the more or less, that is decided by Set-Jeffs rule. Plus you are getting potassium chloride water here, potassium chloride water. Now according to Set-Jeffs rule, an alkene is produced, which is more alkyl substituted. According to Set-Jeffs rules, you will get an alkene which is more alkyl substituted. So here there is a functional group, it has got one alkyl group. Here it is a functional group, two alkyl groups. So but1 will be, it is found to be minor product at 19%, and this is 81%. So when a secondary or tertiary alcohol is dehydrated, or when a secondary alkyl halide or tertiary alkyl halide is dehydrohalogenated, you will get an alkene which is more alkyl substituted. This is governed by what is called Set-Jeffs rule. So in both the cases, you will get but 1-ene less amount that is only about 19%, but butadiene you will get more amount, that is about 81%. This is all about today. Next time we will discuss more.